Okay, assume that this device to be operated at condition whereby there is no heatsink to be attached. You can see that in the front page, it shows that your device here, this is non-control device diode. It shows over there that I average can go to up to 8 ampere. But as I mentioned before, this is good to be true because it will tell the good side of the device. No? But how actually maximum current it can go pump in is up to your justification. So we consider at this device without heatsink to be attached to the system. So there will be this kind of diagram. You have a junction temperature and ambient. So here will be R theta JA. This is your PD. And what we have discussed inside the pre-recorded slide, without using the generic formula would be DJ equal to PD R thermal JA plus TA. And assume that for this condition, or in any of your case, you can assume or you can consider your ambient. If not given, you can consider or you can assume by yourself based on what are your application. Maybe if you're going to use in the cockpit of your electric vehicles or whatsoever, maybe the ambient temperature will be quite high, can reach up to 40 degrees C. Or maybe in the room, in case in a operating room whatsoever, maybe can increase to up to 35 or 30 degrees C. And it is impossible for you all to maintain your operating condition in the room temperature 25 or 27. So assume TA now as 40, let's say. So your TA is 40. So you open your data sheet, you can see that your TJ, we try to find out what is the maximum limit. What is the maximum limit if without heatsink? So without heatsink, what is the I average max or the maximum current that the switch should be limit to? Okay, TJ, if you open your data sheet, page number 1, bottom in the table, it mentioned about the operating junction temperature, also operate storage temperature, which is 150. 150. So we try to find out what is the PD max. So R theta JA also mentioned over there in the datasheet, which is in the page number 2. A certain datasheet they mention in R theta. Certain datasheet they mention in R TH. Both can be used. Same goes to some datasheet they mention in degree C. Meanwhile, some mention in Kelvin. Both carry the same range. You can use any of it. So R thermal JA, thermal resistance from junction to ambient. You can see from the data sheet it is 60. So plus 40. So you will get your PD at 150 minus 40 divided by 60. How much you get? 1.83, is it? You can interrupt any time. Anything that you miss or you lost or you any concern, you can interrupt anytime. Please voice out because I'm not looking at the message regularly, so please voice out here. So everybody okay, yeah? 1.83 watts. Semua dengar kan ni? Anybody? Okay. I'm afraid that I'm talking alone. Okay, 1.83 watt. This is the maximum PD. The maximum not it's about the losses that the switch can withstand. The heat that generate here, maximum it can raise up to 1.83 watts. Not about, we are not focusing about how much the current or the power delivered to the load. This is the losses that the switch can withstand. Means that within this dissipated power, within the processing condition, it can dissipate up to this value. If more than this, the junction will rise more than 150, so you will burn your device. So 1.83 watt. So 1.83 watts, how many ampere actually? And so how many ampere? So for semi-control or fully controlled device, you will have a direct plotting graph of PD versus I. So if you open your datasheet number 1, page 3, we have table figure 2 and figure 3. You can see over there, PF versus IF. P forward versus I forward average. So now we just follow or refer to figure number 2. Okay, we have PD of 1.83 and 1.83. So when we plot on the graph, you can see that with 1.83, it's around 1.5 ampere, is it? So 1.5 ampere. So you get your I average is 1.5 ampere like that. So this is just about an estimation of projection. We're not focusing on how to details out to find out what is the exact value here, but it is about projection. Means that if you work your circuit within this current 1.5 ampere, so you will get 1.83 watts of losses, heat losses at your switch here. If you pump in more than this, so you would damage your switch already, because the heat will increase more than 150 and it will burn your switch. So our main concern is here is that the TJ. So TJ comes from PD. PD contributed by your I average or I RMS. It depends on the datasheet. If your datasheet mentioned in RMS, you have to find out the RMS current here. If you just need average, so average is sufficient. And RMS, huh? So, and some more, if you have already the current value, so you can use current value to get your PD, or you calculate your PD, and you get your TJ. And some more, if you don't have your current, so it comes from other kind of converter, so you have to find out how to, what is formula need to be used to find out your I RMS or I average. Let's say you have a cycloconverter or you have an inverter, and we convert from DC to AC, or you have rectifier, but which you have learned before, and or you have a DC to DC converter, DC to DC buck boost or whatsoever. So you have to use this formula of the dedicated converter to get your I RMS or I average. From there, you can calculate or plot. And if you use semi or non-control device, you can get directly from the graph. If you are using a MOSFET, IGBT or whatsoever, you have to calculate. And so direct or you have to calculate. So you have to calculate. And okay. Okay, this is the condition whereby we don't have or we don't put or we don't apply any kind of fixing to the device. Okay, means that we have to limit our switch current down to 1.5 or up to 1.5, sorry, up to 1.5 ampere. We cannot use up to 8 ampere. This is the maximum you can pump into your device. Okay, let's say if you want to put in the heatsink, so such that we can improve further. and up to the maximum spec that the device have. And so for 8 ampere, how big actually? And in general, how big actually the heatsink we need to attach to the device? So we calculate for the scenario. Okay, same BY229 with heatsink. With heatsink, it will be rectifier. So just now is without heatsink. So you have your rectifier. So you have your metal tab. So we don't attach any heatsink. So your circuit will be one element. But if you put a heatsink back here, I mean at the back here you have a heatsink. So it will be 3 elements. 1, 2, 3. 3 elements. So the heat which is generated here will go through from your junction to ambient throughout your case and also your heatsink. So here is your thermal JC, our thermal CS. This is our thermal SA. So 3 elements. So where comes this another 2 element is from? You have a heat sink here. You have a heat sink here. In between heat sink and your metal tab, there will be what's so-called thermal paste, which be thermal paste or thermal pad, which used to firmly intact attach your heat sink to the metal tab. The lower, the better, and the, in terms of thermal resistance value. So in general, the formula will be Tj is equal to Td R thermal Jc plus R thermal Cs plus R thermal Sa plus Ta. So each of value for the material or for the component here comes from different datasheet actually. This one comes from manufacturer of the device. This one comes from the manufacturer of the thermal pad. This one comes from the manufacturer of your heatsink. And so our focus now is that this BY229, it said that it can conduct up to 8 ampere. Is it? So in terms of applying your circuit with 8 ampere, how big actually? How big this heatsink should be attached to the device? And how big this heatsink is? So again, we put in the spec that we have for the device, the limit, which is Tj at 150. So PD, we try to find out what is the PD applicable for this device at this scenario. RJC, you open your datasheet, first datasheet number 1 at page number 2. R thermal J to mounting base, that is RJC, which is 2.0. 2.0. RCS, normally we provided, and in generic for the thermal pad we use 0.5. If there is a better spec, so you can use that one. So 0.5. So this is our thermal SA, that is the unknown that we looking for. Ambient we assume at 40 now. So this PD we need to find out. Okay. For MOSFET, For BY, semi or uncontrolled device, you can directly plot from the graph, which is if you get, you need 8 ampere, so 8 ampere here, you will get your, on page number 3, 8 ampere at duty cycle of 1. We assume at worst case scenario. So 8 ampere, you will go down to, or you go up to, sorry, here is, this is your P, this is your A current. So 8 ampere, you go up to 10, 12, 12 watt. Is it? Figure number 2. Figure number 2. Table number 2 in your data sheet number 1 here. This data sheet. Figure number 2. So for 8 ampere, it rises up to 12 watts. And 12 watts. Huh? So 12 watts. So you put in that 12 watt into your calculation. So we'll get the value of the heatsink that we need. Okay, 150 equal to 12 times 2.0 plus 0.5 plus our thermal SA plus 40. So this is the final value for the thermal SA, which is how much? Anybody can calculate? 150 minus 40 divided by 12 minus 2 minus 0.5. So you will get 6.67 degrees C per watt of heatsink that required. Is it? Anybody? So if the available is 6 degrees C per watt only, so is it okay or not okay? If let's say I try to search from the market, we have only 6 degrees C per watts of heatsink. So is it okay or not? Anybody?
Yeah, it should be okay.
Should be okay, huh?
Yes.
Okay, we want to make sure that okay or not okay, we put in back the value into calculation. So we take TJ as unknown. So we put in our PD, our thermal JC, our thermal CS, and the value of 6 degrees C per watt just now, plus ambient. So we will get the TJ which is less than 150. Means that better lah kan? Because the heat now is no more 150, maybe reach down to 140, 130. So the heat is lesser than the maximum, should be okay. Okay. So that's the in terms of what's so called or semi-control device. Semi-control device, we have the ability of when we know our current, how much current we want to use, we can probe directly how much actually the losses which happen inside the device. We can get or acquire our PD. Okay, now if we use the fully controlled device such as MOSFET, IGBT, GTO, whatever, so they or manufacturer will not provide this kind of graph. We have to calculate, which is P loss is equal to I square R. Okay, you open your datasheet number 4. We go to datasheet number 4, which refer to datasheet number 4, MOSFET, IRF 6330, if I'm not mistaken. Yeah, IRF 630. Okay, take note that different manufacturer, maybe they retain the same part number. But if you open or you take a look at the dedicated datasheet, there will be a few or distinctly what's it called, different in terms of resistance, in terms of performance, limitation. The function is the same, but when you involve different manufacturer, so you have to refer to your dedicated manufacturer punya datasheet lah. So we go to datasheet number 4. Okay, now we are talking about IRF 630. Apa ini? Okay. Okay, datasheet number 4. It's better for you all to print out, because you can flip back and forth your datasheet for design purpose. IRF 630. So over there you have we have maybe same part number. The initial part number is the same, but the package or the orientation or the body shape of the device will be slightly different, because same performance, maybe you want to use under or within different kind of package. Maybe you want to have a compact package, so you may buy the SMD parts, surface mount type. Or if you are able to have a space which can put more parts or larger space, you can opt to have a TO220AB, like that. Maybe you can put more bigger heatsink, so you can push in more current. So over here we have a dashboard which shows us that this device can go up to 9.3 ampere, kan? But it's not like that lah. And because when we evaluate, means that when we calculate or look further into the datasheet, this 9.3 ampere comes with condition lah. If you run under room temperature or whatsoever, so you can reach up to 9.3 ampere. If not, you have to limit by yourself. You have to limit by yourself. So there's two basic way that I've taught you on how to probe or how to justify on the maximum limitation of the switch. Is that you have to justify if without heatsink, how much the current can conduct into that switch. And some more is with heatsink, which involve minimum three elements here. So how big the heatsink is. And so now we try to consider this one. Okay, without heatsink, you have a heat that generate at junction. We have to release to the ambient. So we go through thermal JA. And within the PD that generate here, we have to deliver or convey all the heat from junction to ambient. And without heatsink means that it generate or disperse just from the metal tap. And we have here your MOSFET, your metal tap here, just disperse directly to the ambient from junction to ambient, and Tj to MTA, and so without any intermediate or heat sink. Okay, the formula is the same. Tj is equal to PD R thermal Ja, because from junction to ambient, plus Ta. The same, we assume that our ambient now is at 40. So we open your datasheet for this parts. It shows that your maximum storage and maximum junction operating temperature should be limited to 175. 175 is not low, because 100 degrees already you can boil up the water. So 175 is very huge, very high. So 175, this is just to estimate our maximum current that should be pumped into the device. To R thermal Ja. How much R thermal Ja for this device? You can open page number 2. The last table there, thermal resistance parameters, degree C per watt, R thermal JC, R thermal CS, R thermal Ja. We have two values for R thermal Ja. On the parameter, you can see node 4 and node 5. So junction to ambient, node 5 too, if you mount on the PCB, means that you have, or you use the PCB type device. If number 4 node is referred to what, you can open the last page for node number 4. This is only applied to TO220AB package, which is on the page number 1. It refers to the part, the first part, which has the metal tag like this. So this is the 2200AB. 2200AB package type to TO220 type. TO220. So it shows that this R thermal Ja is 62. 62. UC per watt plus 40. So what are the PD max if without heat sink being used? So PD max here is 175 minus 40 divide by 62. You will get 2.17. 2.17 watt. So this is maximum dissipated power that this switch can withstand. So this is the maximum power this switch can withstand. So the heat, you cannot exceed 2 watts. So on these 2 watts, actually how much the current? Because our concern, as we mentioned just now, TJ is our main concern. TJ comes from PD. PD comes from I. So I, you have to calculate, or you can get directly from the application. For your assignment wise, this I you can measure, means that you can put an emitter when you compose your circuit. You can put emitter, you can measure here what an average RMS, so you can put inside your calculation, or you can calculate by calculation of your converter, DC-DC converter, whatever, you can put inside here. So there's 2 ways. Either you measure up or you calculate. So from that, you can get your PD. So PD is up to you. If you use a non or semi-control device, you can use graph, and can use graph to have your PD, or you have, if you use later on the MOSFET, fully controlled, it's equal to I square R. Okay, for this device, PD is 2.17 watt. So this is your MOSFET. So how much actually your current? Okay, PD is equal to I square R. So this is your MOSFET. We have D, which is drain, and source. Here is your gate. So when you operate from drain to source, there will be, when you switch on, there will be a resistance. So this is your RDS on. During on stage, there will be a resistance, RDS on. And RDS on is depend on temperature. Okay, as per mentioned inside your datasheet, for this part, RDS on is 0.30 ohm. And 0.30 ohm. This value is applicable when your temperature of the device at room temperature, which is 25 degrees C. If you take a look at your datasheet, page number 3. Page number 3, figure 4. Figure 4. It will show you the normalized on resistance versus temperature. And normalized drain to source resistance.
Tak ada lah. Cuba hitam sana ni.
Okay, you can see from the datasheet. Figure number 4. I'm not able to open the datasheet here. So it shows you the normalized on resistance versus temperature. R normalized versus temperature. So you have temperature here. You have R normalized here. Means that this temperature of 25 will give you 1.0 of the value. So means that 1.0 times 0.3. It happened only, the 0.3 ohm happened only here at temperature of 25 degrees C. Now, if you want to use at maximum temperature, which is 175 degrees C, so it happened to be your normalized value is normal at 1.0. The value will be here, which is, if you refer to your datasheet, it's around 3.2 or 3.1. 175, so around 3.1. We are not looking at the exact value, but we are talking about estimation and projection. So around 3.1. So your RDS on at 175 degree is equal to 3.1 times 0.3 ohm. So dia akan jadi apa? 3.1 times 0.30. 0.93. So 0.93 ohm. So 0.93 ohm. Next slide tadi. So 0.93 ohm. So this is your RDS on. So RDS on at 175 degrees C. So you will have your value, which is PD max, we just calculate just now, 2.17 I square RDS on is how much we calculate? 0.93. 0.93. So this is your Imax. That should not be exceeded for this scenario with this, which is you're operating without a heatsink. And without heatsink, we don't put any heatsink. So the I will be 2.17 divided by 0.93. So dapat 1.57, 1.53 M. Is it correct? 1.53 ampere. Instead of 9.3 ampere, we are able to conduct the circuit, the current in the circuit up to 1.53 ampere. So means that if you conduct more than 1.53, the temperature, the PD will rise, and the temperature will rise above 175. So we have to limit our current application down to, or up to 1.53, sorry, up to 1.53. If less than that, so it should be okay. Okay, this is the maximum limit of the switch for IRF 630 if we apply no heatsink to the application. Okay, everybody okay? Any question? You have to interrupt me because I'm not looking at the message. Anything you just ask from here.
Okay, sir. Okay.
Okay, yeah?
Okay.
Okay. Okay, then we proceed. If we now going to use heatsink. So just now we don't put any heatsink, so we try to find out what are the maximum limit in terms of current. Because we cannot pump up to 9.3 for sure. So if you want to use heatsink, if we want to pump up further, up to 9.3, let's say, we try to figure out what is the value of heatsink we need to attach. Because the data sheet say that this can use up to 9.3. So if you want to pump up to 9.3, so how big the heatsink should be? Okay, we put into the next slide of considering this. Okay, when you okay, the same part number is now number 4. Datasheet number 4, which is IRF 630. Okay, with heatsink. So the circuit will be the source of heat, element of RJC, element of CS, and element of SA. So TJ here, ambient is here. This is your case. This is your heatsink. So R thermal JC, R thermal CS, R thermal SA. So 3 elements. So this is your PD. Okay, with heatsink, as we discussed inside the pre-recorded lecture, TJ is equal to PD. From this circuit, you can generate the formula. R thermal JC plus R thermal CS plus R thermal SA plus TA. Okay, we put back the spec that we acquired from the datasheet. Number 4, TJ max is 175. Did you see? PD is what we're looking for. Sorry, PD we calculate and put in around. Because we are going to use heatsink, so we are not going to use R thermal JA. So we use R thermal JC because we conducting the heat from junction to case to heatsink, heatsink to ambient. So look at data sheet, page number 2. R thermal JC is 1.83. 1.83. R thermal CS Also mentioned inside the data sheet, 0.5. Thermal SA, and this is the heatsink value that we need to find out. And this is the unknown for the time being. T ambient is 40 degrees C. So how much PD actually? And PD is the unknown that we have to investigate. And PD is equal to I square RDS on. Okay, because we are considering at 175 degrees, so RDS on will at 175. And so how much is now we find RDS on 175? Which is 0.93 kan, 0.93 ohm. RDS 0.93. So I is the maximum current, 9.3 square, 0.93. So how much is the PD? So the value is around 60.43 watts. 60 watt. Happen that the losses that emitted from this device at this point is 60 watts. 60 watt. And almost reaching 62 watts maximum power dissipation, which is mentioned in the first page of the data sheet. So 60 watt. We try to find out how big actually the heatsink when 60 watt of dissipated losses here happen, how big the heatsink we should provide. Okay, put back the value inside the formula. So we will get our R thermal SA, which is 175 minus 40 divide by 80.43 minus 1.83 minus 0.5. You will get C negative 0.65. Is it? Negative 0.65. Mean less than 0 and below 0 and below 0. So is it possible to get this kind of heatsink?
No.
What does it mean by this negative value here? So this negative value means that you have to force cool your device. Not enough just to put in an effective device that can disperse all the heat that generated there, but you have to put in, let's say you have to put ice on the heatsink. Get me or not? So it is impossible to provide this kind of heatsink or heat management to the device. So it means that you cannot pump in 9.3 ampere to the device and for this application. Okay, any question from the floor?
Sir, I got one question about the ambient temperature, right?
Yeah.
So, if I assume the ambient temperature to 25 degrees, is it possible?
Data sheet, they assume that you can provide 25 degrees C to the ambient, but
Yeah.
it is impossible for in terms of when we produce the power supply. Let's say we assume that our customer or our operator are able to maintain that temperature. So it is dangerous for you to assume that they will buy our product and they will operate our product within room temperature. Because
Okay.
when we produce, we for sure we provide in terms of warranty. Anything happen within 1 year, you can refund to us, you can return to us, we give you free refund, replace. So if you assume in the first place like that, once you deliver to the market, you have more recall back, recall, and end up you close your company. So that's the dangerous thing lah.
Okay. So
If
the
let's
most
say we are producing for our own usage, so it's okay because we can control. So that's the concern. Okay.
So this year got any minimum requirement for the ambient temperature for this assignment?
So in terms of design, we try to use worst case scenario. So means that worst case we cannot use up to this. We cannot pump up to this level. Let's say okay, if we can negotiate, means that we can maintain or we can enforce the user or the end user to maybe within let's say we can put any kind of control so that we can reduce ambient temperature down to 30, let's say 35, means that we provide any kind of suggestion for the end user to form, and that we can reduce. So you can use lah.
For 30 degrees is okay lah, right?
30 is okay.
Okay. That's all. Thank you.
This is just to exaggerate.
Okay.
Yeah.
Thank you, sir.
Okay, and then next we go to almost time. Go to the example. The example that I left you before is on the this one. DC-DC converter which operate at temperature of 100 degrees C. Okay, 100 degrees C with a common heatsink. Commons mean that we attach all the switch to one heatsink. Okay, one heatsink to occupy all the switch. Means that we have a heatsink here. All the involved switch is attached here. We have switch number 1, switch number 2 attached to the single heatsink. Individual heatsink or individual heatsink will be like this. Means each switch has its own heatsink. Okay, for this example, we consider that the TJ of the MOSFET here is at 100 degrees C. So if we want to operate at 100 degrees C, so what happened to the other spec or scenario of the switch? So when we redraw in terms of thermal circuit, so they'll be like this. So one MOSFET, one rectifier will share one heatsink, and from temperature of junction of the MOSFET, it goes to the ambient through the same heatsink which the rectifier is using. Okay, go to the ambient. So we have to furnish all the values here. What is value here, over here, heatsink value at this point. Is it sufficient or not, the heatsink, to operate this MOSFET at this scenario? So as I mentioned before, we need to find out what are the current that flows through this MOSFET. Then you are able to know what's the PD and the steps that from the circuit. We find out what is our AI, and then PD, then also on the TJ. And so with that, we are able to conclude, is it enough or not, sufficient or not, the heatsink for the system. Okay, if you open your, I have uploaded the solution for question or example here inside your, I think I forward to the WhatsApp. I haven't uploaded to the Google Classroom. I will upload later for those who have not. So what the step is that when you get this kind of question, you have to draw the illustration of how the layout would be of your thermal circuit. So we have one MOSFET and one MOSFET, so one element. Another one is your rectifier. So this is your TJ MOSFET. This is your TJ rectifier. Because they share the same heatsink, so there will be only one heatsink. And at the same time, by right, you have two elements here. One is your R thermal JC, and this is your R thermal JC as well. Here you should have R thermal CS, but when we apply this kind of device, which is directly attached, means that your device is attached directly to the heatsink. Solder means that you don't put any kind of solder paste in between your heatsink and your device. It attached directly because we are putting the device of a SMD part. You can see that here. RCS is 0, means there is no resistance between your case to your heatsink. We are using SMD parts, and you can refer to your datasheet. So refer to the SMD parts. Okay, so there's no element between your heatsink to your case. So means that your TC is equal to TS. Okay, here is your thermal SA from heatsink to ambient. So this is your ambient. Okay, for this part, we solve the circuit analysis one by one. We use MOSFET as our reference. So the worst case scenario is that the MOSFET is operating at maximum duty cycle of 0.6, and this is your duty cycle maximum, which is at 0.6, and voltage is 100 volts. Ambient temperature 50 degrees C. Is it? Ambient 50 degrees C. Your load resistance is 10 ohm. Switching frequency 40 kilohertz. 40 kilohertz. Later on, we will see that actually there is two source of losses, and two source of losses. I will catch up my lecture because we are almost 4:30 already. Okay, there is two kind of losses. For power supply or power processing system, the PD, which is equal to IDRS on, is for the conduction loss. Meanwhile, we have another contribution of losses which come from switching. So for switching power supply which operate below, let's say 10 kilohertz or 1 kilohertz and below, the switching kind of losses is not so dominant. But when you increase more than that, 100 kilohertz and above, so the switching losses which contribute to the total losses should put into account. And we cannot push like the signal processing device or signal processing system, which operate can go up to maybe megahertz, gigahertz, and we have now 4G, 5G. Because once we hit above, let's say 100 kilohertz, the dominancy of the losses is huge. So normally we reduce or we limit up to 100 of kilohertz of switching. And for power processing system which conducts or which process high current system. Okay, P conduction and P switching. So the device which used inside the power processor like this, we have to consider in terms of their heat dissipate at the when operate within the system, It should be maintained or below or at certain level of temperature. Okay, the contributing power or losses in the switching mode is happen during transition when you switch on or switch off. Okay, when we switch on means that across the switch, the voltage will drop from VDS to 0. And we put a gate, we switch a gate, and when we put a signal to the gate, means that if we have a MOSFET, this happen on a fully controlled device as I mentioned before. And we have a MOSFET or IGBT. We have a gate here, and we want to switch on between drain to source and between drain to source. So we have a resistance, which is RDS turning on. Across the gate, when we switch on, VDS will drop and from withstanding voltage down to 0. Meanwhile, we apply the gate here with a gating signal. We put a gating, it will slowly gate on, and at the same time, the VDS will reduce to 0. But it will not happen drastically. So there will be a transition between voltage drop and voltage up here. So there will be a transition between the current as well. And we drop at the same time, I which conducts to the through the device is increasing. So there will be overlaps. So these overlaps introduce losses. Losses during switch on, losses during switch off. And so how this losses is calculated? We divide by 2, P on and P off. P on is the energy of switching on times how many you switch in one cycle and the frequency. This E on is the amount of I that delivered throughout the circuit during on stage times the VDD here and divide by 2 and times T on divide by 2. So T on you can have the value of T on or T delay on plus T rise from the datasheet. Each of the datasheet will provide you how much or how about the performance of these two values here. Same goes to P off. So actually your P on, if you rearrange the formula, will be VDD and I on times F switching divided by 2 times T on plus T rise. So this is the total formula for your P on. Same goes to P off. P off is equal to VDD I on F switching divided by 2 times T delay on, delay off, TD off plus TF. This value you can get from your datasheet and switching from the operational condition. VDD and I on you get from your calculation. VDD is from the scenario. Divide by 2 you can will get your P on and P off. So P on plus P off is your P switching here. And so P switching plus your P switching plus your conduction loss, which is this one. So we contribute to the P total and PD total. So when you operate your system within 100 kilohertz and above, so you have to consider this P switching inside your calculation of losses. So you have to perform this step inside your assignment and sum up 2 element into your PD. Okay. Okay, back to the example just now. For MOSFET, seems that the MOSFET is conducting at 0.6 duty cycle, and when the MOSFET conducts, the duty cycle will off, and when it's off, the rectifier will on. So at worst case scenario, MOSFET will conduct at 0.6 duty cycle. So at that time, rectifier will conduct at 0.4. During this one on, this one off, this one on, off, this one on. So what happens is that we have to find out what are the average in terms of voltage of the MOSFET, because we want to find out what is the current that flow through the circuit or the MOSFET. So we found out the average current because it operates at duty cycle of 0.6. So 0.6 times 100, we get 60 volt. So average current is the amount of average voltage divided by 10, our resistance value. So we get 6 ampere. So 6 ampere go through your MOSFET. And meanwhile, for a rectifier, we have a 0.4 duty cycle times the average current that flow through your system. So we get 2.4 ampere. And so actually from 2.4 ampere, if you take a look at datasheet number 1, we can probe directly the losses, because I mentioned before, for semi-control device, you can get your PD with your average current. This is your PD, this is your current. So once you know your current, you can get your PD. And so rectifier, you can get your PD. Or you can use form factor. Form factor or dimension inside the datasheet as well is the value of a scenario which happen when you know your RMS divided by our average. So you get your form factor. So form factor table you can use, or you can use directly the average current to get your PD. So but for rectifier you have to calculate. So here, if you have a form factor table, you refer to form factor table. You have 2.4 ampere, you can get directly your PD and dissipated power. For MOSFET, you have to calculate. And ID MOSFET just now we have 6 ampere, but in the datasheet it requires us to perform or calculate using RMS. So we have to times D in duty cycle, set it, and use the average current value. Multiple to the average current value, we get 4.65 ampere. Okay, based on the graph for datasheet number 4 is now, this one is NTD 12 and 10. If you refer to your datasheet, and this is datasheet number 3 if I'm not mistaken, NTD here. So it shows that you have a 0.14 ohm RDS on during temperature room condition, 0.15 and 0.15. But if the scenario now we are going to use at above above room temperature. So at room temperature, the normalized factor is 1.0. If we use at temperature above, let's say a maximum of 125, and so the normalized value is no more at 1.0. The normalized value becomes now 1.87 or 1.87 like that. So means that you have to times 1.87 to the normalized value. That's why we have RDS on of what is the normalized value times RDS at this value. So this is RDS at this value, 0.14. This is your normalized factor. So you get your PD MOSFET and For this scenario, the MOSFET will operate at 100 degrees C. So you find what the RMS squared times RDS on at 100 degrees C. So 100 degrees C is here. So 1.65 times 0.14. And that's why we can see from the solution. PD is 4.65 times 0.2275. And you can, or 2725. And so PD is equal to 4.92. 4.92 watt. .92 watts. So PD is 4.92 watts. So we need to find the parameters here, which happen here. So RJC TMOS 100, RJC already available. So what's the TC? And TC is equal to PD times R thermal JC plus TC. Sorry, it's not TC, TJ here. TJ is equal to, so 100 is equal to the PD, we got more 4.92, RJC 2.65 plus TC. So you got your TC is 86.96 degrees C. So this is your TC. So you have your MOSFET, you have your RJC, you have your TC. Then we try to find out what is the TJ of the rectifier. So we go to the rectifier. So TJ rectifier is equal to P, which emit by the rectifier, PD rectifier, R thermal JC of the rectifier, plus TC. So we have just now a rectifier is 2.4 ampere. P rectifier is 3.75 watt. 3.75. RJC also available inside your data sheet of the rectifier. So TC is just now 86.96. So this is your TJ for the rectifier, 94.46 degrees C. So you have your TJ MOS, TJ rectifier, R thermal JC. Now we try to find out what is the R thermal SA. So at this point, TS is equal to PD, and PD which comes from here and also here is the PD sum or PD total times R thermal SA plus TA. So you solve this one. TS you put in here. TS is the same as TC because we are sharing the same point. $86.96. PD is the PD total. So how much the PD total is now? PD of your rectifier, which is 3.75 plus PD of your MOSFET, which is 4.92. So this is PD. Times RSA plus 50. So it will end up that your thermal heat sink is 4.26 degrees C per watt. So the scenario just now shows that, it mentioned that your thermal heat sink value provided with 3 degrees C per watt spec. So is it sufficient or not to operate or to limit your MOSFET junction temperature up to 100 degrees C? So the MOSFET, the heatsink is sufficient or not? So 3 degrees C is okay or not? So okay or not? Anybody? Yes?
Yeah, it's okay.
Okay, because we need 4.236 degrees C per watt, but we have, or we've been provided with 3 degrees C per watt. So means that we have now is the better heatsink, and the lesser the resistance is the better one. Because if you put in again to the formula, we can see that with this kind of heatsink, the TJ or the TS will be lower. When the TS is lower, TJ rectifier also will be lower, and TJ MOS also will be lower. So the lower the operating temperature is better for the system. Okay, you can try on the example on the slide that I give you. Simple DC converter operates at 100 kHz, conduct maximum only 1 ampere. So here the value is given, so you don't need to calculate. Justify the requirement of heatsink for the application. So it's just about if you apply this kind of heatsink, how much current you can conduct to that device. If you don't apply heatsink, how much the safe level of current you need to limit to a certain device, such that the main thing, which is TJ, and your TJ here is not exceeded, and you tak melebihi maksimum TJ ataupun TJ yang dikendaki oleh kita lah. Kita nak update TJ dia kan pada berapa punya value, so that TJ is not exceeded, tak lebih, so it's okay lah. Okay, any question? We have reached to the end of lecture. So if there is anything, I'll try to record and upload again to the YouTube, and I inform you all. Regarding your attendance, please copy, go to the link. I paste it here. Please open the link and fill in accordingly. Okay, any question from the floor?
No, sir.
No. Okay, next week will be your exam. Coming week, I'm not sure which date. So the question will be 4 questions, one from me, and you will need to answer one by one. We provide, let's say, 20 minutes or 25 minutes for question 1. So all of you have to answer question 1. When end of 20 minutes, you have to submit, and we provide you another question of question 2. Then you will have to answer all question 2, you submit, then we provide you question 3 accordingly. So one by one. So you have no option unless except to answer one by one, following question by question lah. So my question will be the last question. Okay. Okay. Hope you can do better in your exam. Anything?
So for the exam, we still need to screenshot or I mean we need to take the photo of our handwriting also, right?
Yeah.
And upload it over there.
You download your what's it called cam recorder. What nama tu?
Yeah, I know.
And convert to PDF kan? PDF so you snap, convert to PDF, you upload to the portal, to the classroom, Google Classroom at that time.
Oh. So
Okay.
the time got give any extension if we encounter the problem of the internet?